The final speaker for the night, and he's final because absolutely no one wants to follow him, is the madman of Perl. He's here to speak to us, and I know I'm getting this title wrong, on Temporally Quaquaversal virtual nanomachine programming in multiple topologically connected quantum-relativistic parallel time spaces made easy. Please welcome Damian Conway.
Thank you. It's great to be back here. Do I have slides? I do indeed. Excellent. I'm just thrilled to be back here. You know, it's 2 years since I've been here. I have to say it only really feels like 1 year. And I guess you're wondering, what did I learn in that time that I was away? And I think the main thing that I learned was, don't cross O'Reilly. I didn't turn up last year, and that made Tim very angry. And you wouldn't like Tim when he's angry. Because he gets to say who's doing the speeches before you get up on stage. So he starts off with one of the rock stars of the open source community, who just also, of course, happens to be a cosmonaut. You know, this is the first African in space. This is the guy that has Nelson Mandela's personal number and calls him from the space station. It's Quaquaversal. And if that's not bad enough, who does he bring on second? Well, he brings on the smartest guy in the entire universe. So this is a guy whose brain is so huge, whose head is so full of ideas and humour that there isn't even room on it for hair follicles. And whenever you're up there listening to him, it's like reading some graphic novel. Where there's some great adventure going on back in the 1500s. And Pope Gregory sends him off after something, and it just goes on. And people die along the way, but eventually they come back with the prize, and then the genre changes on you. Then death figures in it, and then it just goes on some more. And the Pope takes the stuff and hides it away, and it turns out to be kryptonite. And now it's in the hands of Left Clunsel. So how do you contend with that? Well, I guess I could have shaved my head and become an evil super genius. And when it comes to being in orbit, well, I've been there. And when it comes to being a billionaire playboy scientist superhero, I've done that. Twice. But I have to tell you, it makes you think. I was almost tempted tonight to get up here and get serious. I was almost tempted to do this talk instead. This was going to be a deep and powerful exposition of the myths of open source software, the communal delusions that we have about it. And basically I was going to deconstruct all of those lovely slogans that we have that Ronald showed me. I was going to point out, well, you know, in theory this is a great idea, but in practice the reality is and we're fond of saying, you know, good, cheap, fast, spaghetti too, where in reality it's kind of and this one, this trope, information, whenever I see this, that's like saying to me, beer wasn't So when you are like me a presenter and you have to follow guys that are as deep and profound and world-changing as that, there's a little evil angel that lands on your shoulder. And it says to you, you know what, Damian, you're not just an amazing hacker, you're also a deep and perceptive thinker. So you get to the stage where you want to be seen as being astute, in the way that Tim is, or insightful, like Paul, or profound, like Lawrence, or just plain serious, like Eben. And as far as I can tell, there are only for me 4 problems with that. They're really not my strengths. I'm not so good at analysing reality. My strength comes more in manipulating reality, mainly through language. And of course, the kind of people that do this is why we use the term wizards when we're referring to people who do hacking. So I like to do some pretty serious incantations in all sorts of languages, including Ronald's favourites, and the space languages. But one of the lies that we tell ourselves is that smart is distributive. Genius is a vector, not a field. The expectation that just because you're good at one thing, that means you're going to be good at something else, all too often proves not to be true. So you've got a guy like this, who's an extraordinary athlete when it comes to basketball. As a baseballer, not so much. Or you've got someone like Wittgenstein, one of the most deep thinkers on free will and language of all time, but an absolutely lousy house painter. And the less that is said about his career as an Elvis impersonator, the better. You've got that fine thespian, trying to make his way as a rock star and not quite making it. And then going back to film and kind of becoming like a caricature of himself. And even someone like Stephen Hawking, probably the greatest mind alive today, frankly, a B-grade actor. And unquestionably, the worst showgirl of all time. So thinking that you can transfer your skills from one domain to another is an infallible sign of aging. And while we're on the topic of aging, have you ever noticed Larry Wall doesn't? If you go and Google images of Larry Wall, you get pictures like this. Now let's just take the 2 end ones there and blow up a little bit. And if you look at pictures of me in the same time frame, as soon as I come to the open source convention and start getting involved in Perl, watch the hair. This is a picture of Alan Turing taken during the war. Look at his team from Bletchley Park. If you go back in European history, here's a very famous picture of two of the great composers of the age meeting. There was in fact a third musician there, one Lawrence Mahler. Going back in your own history here in the States, there were three Wright brothers. You don't wonder why they never talk about Ada Lovelace's husband. You go to the Louvre, they have these little statues up the top commemorating all the great French philosophers and scientists, Fontaine, Ferron, Molière, and then you get to Blaise Pascal. And it does not matter how far back you go in history, all the way back to ancient Egypt. And you see the legend of La-Re-Tep. Well, I think this explains a couple of things. The fact this guy's 7,000 years old, for a start, it explains perl 5. But it also, curiously, explains perl 6. Tell ourselves, and one of those infallible signs of aging is this delusion that your expertise is transferable across different domains. Fortunately, I also have a good angel to dispel the bad one, and it says things to me like this: look, just leave that killer social commentary to the mental giants of the open source world. Stick at what you're good at. So I think to myself, what is that I'm good at? Well, I'm pretty good at geek humour, and I'm very good at photoshopping. And I'm not too bad at hacking physics into scary code. For example, back in 2000, I gave a talk at this convention, although it wasn't held here, where I actually took quantum mechanics and applied that to programming. I talked about the Copenhagen interpretation that if you have a particle that can be in three different states when it's observed, then it's actually in this weird overlay of three states simultaneously until someone does observe it. We call that a superposition. So that you want to think of it as like the yellow one there. And at the time, the world record for the number of simultaneous qubits that were available to do quantum computation was 5. Now, of course, we have a massive 27 that we can use. So I don't think Moore's law is quite working there as it should. But I suggested back in 2000, if we could superimpose arbitrary amounts of memory, then we can create new operators for our languages, like any and all. And they would take a list of individual scalar values and superimpose them into a single throbbing value that was all of the different states at once. But it would be a single value, which we call superposition. And you get two kinds of them. Disjunctive superpositions that would try very hard to be in any state that you wanted them to be in. They're kind of like Canadian superpositions. And then you have the conjunctive superpositions that want to be in all states at once. The American superpositions. The point is that if you've got all of these values superimposed, just as in quantum computation, all of the operations applied to them will be done at once. So all of the operations run in constant time, no matter how many different states the thing is in. So for example, you can start off and you can say, I want any 1, 2, 3 times 2. What that looks like diagrammatically is we've got a superposition of 1, 2, 3. We multiply by 2, we now have a superposition of 2, 4, 6. And you can use that result in other computations, and that will keep on mapping the individual states across the operation. So that's really the same as saying any of 1, 2, 3 by 2, which is the same as any of 2 by 4, 6, and then you would parallelize the assignment, the equality test, and you would end up with any of false, true, false. And if any of those are true, then you would print 4. And of course, any of them is true, the middle one is. Now why is that useful? Well, here's something that will test for prime numbers in constant time. And all I need to do is I need to say, take the number n, which you pass in, and modulo it with all of the numbers between 2 and the square root of n. The plus 1 there is just to round it up because you're only going to be able to do it for integers. And when you do that, you get a superposition of all of the moduluses of those results, and you just compare them all with 0 in parallel in constant time. So if I put in the number 23, for example, then I end up saying 23 mod all of 2 to 5, which is 23 mod 2, 3, 4, 5, which is 1, 2, 3, 3. And then you map the not equals across it, and are any of them equal to 0? None of them are, so they all become true. And now you have a superposition that's actually all in one state, so it collapses down to, yes, it's true that this is a prime number. And you did it in constant time. And of course, having given this talk, I implemented it as a perl module, which is available on the CPAN. And then in 2002, I came back and I started talking about general relativity. And I talked about the idea of the light cone. So when you're travelling in space and time, the amount of distance you can travel in a given unit of time is limited by the speed of light. You can't go faster than the speed of light. So in 1 second, the greatest distance you can travel is 1 light second. In 2 seconds, 2 light seconds, and so on and so forth. So you end up with this cone of where can I be in the future if I'm here now? And you can never be outside that cone. And indeed the cone is recursive. At any point in the future, it'll have its own cone that limits where you can be. And so a path is only valid and realistic in the universe if it's always within the light cones on the path. Which means you can't do something like that, because even though it's inside the original light cone and the second light cone, it's outside the third light cone. What does that mean? That means it's trying to travel faster than the speed of light. Which brings us to this guy. Dutch, of course. And in addition to inventing the munchies, he also discovered Lorentz contraction. The idea that as you speed up closer to the speed of light, your actual physical body will shrink in the direction that you're travelling, and time will slow at the same time. And what he really discovered was that if you looked at one of these time-space graphs and looked at an event on them, then accelerating yourself by increasing your velocity is the same as rotating your frame of reference. So if you look at it, you can see that where in the t prime there was a certain x distance, when I rotate, the x distance gets smaller. Lorentz contraction occurs, but at the same time, the dimension of time gets bigger. It slows down. Now what does that have to do with these light cones? Well, it means that we can rotate 2 light cones with respect to each other simply by changing the velocity with respect to each other. Why is that important? Because if you look at the brown trajectory, which belongs to the blue light cone, you'll see that it's fine, it's inside its own light cone, but what's happening with respect to the other light cone? Well, it's transgressing the boundary. It appears to be going faster than the speed of light. And if you twist your 2 light cones enough, you can actually get the trajectory to cross the x-axis, which means it's going backwards in time. And it turns out that you can do this sort of thing with a very strong gravitational field, which bends the space around, twists the light cones, and if you then spin the star, that actually frame drags the entire space around, and if you do it fast enough, you can make the entire trajectory loop round upon itself, not just in space, but in time. So of course at this point, I pointed out that Frank Tipler, the physicist, found a way to do this in 1974. It was quite easy for certain definitions of easy. You simply take a mass 10 times as big as the sun, you compress it down to a neutron star, you extrude it out into an incredibly thin, long cylinder, which you then spin up to a few 100 million RPM. And then there's a very special path that you can navigate around that star, a helical path, that when you get back to the starting position, you will be back to your starting time as well. So then I made a modest proposal, far more modest than Rommel's was, which is that every PC that ships should have a neutronium spindle on the chip. And then we would have one of these closed, time-like loops with a conditional test on it. And of course we all know that a loop with a conditional test on it is a while loop. And this would be a while space-time loop, which is a bit of a mouthful to say, so I abbreviated it to an ST loop, and then I just decided, oh hell, it's a whilst loop. And you could have for loops and until loops, and you'd use the same trick of just putting a T for time on the end of it, and they'd be for and until loops. And then, of course, they all run in 0 time, because you get down the loop and you're back when you started. And of course, I implemented it in perl. So that's what I'm good at. New models, now crazy new models of programming. But I have to be honest with you. We like to think that the progression of these kinds of ideas is this glorious evolution to the pinnacle of creation, the hacker. But the Romans had us nailed. The Romans pointed out that progress requires, effectively, failure. Progress only occurs in the presence of failure. So what I was going to do for this talk was tell you about a promising new technology that turns out to be a promising old technology. It's a technology called rod logic. I love the name because it reminds me of the super science novels that I used to read as a kid back in the 60s. Rod logic is, this young fella just happened to have his own flying atmosphere vehicle. And he kind of gets a bit cocky by the 6th novel, and he's built like an atomic earth blaster, and things start going horribly wrong for him. But what this is really about is not this, but about this guy. Charles Babbage and his analytical engine. A computing device that works by the application of rods and levers and gears and cams. And incidentally, the inspiration for the single best Lego kit of all time. And it was just kind of a quaint historical thing until this guy came along. This is Eric Drexler. I mean, seriously, doesn't it look like Christopher Lee? And he said, hey, you know what? We can take carbon nanotubes, little tiny rods made out of carbon chains, incredibly strong stuff and surprisingly easy to make. And we can take a whole lot of them and lay them out like this, and hook them all up with interatomic bonds, and then we can label the position of one of the ends as being 0. And in fact, the other end as being 1. So if it's to the left, it's 0, if it's to the right, it's 1. And when you have something in this geometry, what happens when you push the left-hand side to 1? Well, this happens. And it goes to 0, and back and forth, and back and forth. It's a NOT gate. A teeny tiny little one. And of course, you can make OR gates. What I love about them is they actually look like OR gates. Because if you push either of the inputs forward, you get 1. And if you push them both forward, you get 1. And you can have an AND gate. And the AND gate's got a little teeter-totter on it. So if you push one of the gates forward, it doesn't push the other one far enough. It doesn't matter which one you do, you've got to push both of them forward to get a 1. That's an AND gate. And once you've got those, you can build anything you like at atomic scale. So I was thinking, that's going to make a great talk at OSCon. If only I could make it work with perl. Now, perl's pretty good at small programs. So I thought, how could I get perl programs that only use little rods? And of course it was obvious as soon as I thought that, well, perl programs do have little rods in them. The minus sign, the underscore, the vertical bar, the 2 slashes. It has bent rods in both directions. It has 3-way bent rods. So in other words, what I wanted to do was create a little module, and it's a very little module. And I create 2 subroutines, one of which is called double underscore, and one of which is called triple underscore. And double underscore does output, and triple underscore does input. And once you have that, you can start writing programs in pure rod logic. So this is the program that prints 0, and indeed it prints 0. And of course, because in perl there's more than one way of doing it, this also prints 0. And so does this, and so does this, and so does this. And to print 1, you can do that, or that, or that. They all print 1. That one's a cool one, I like that one. And then you can build a NOT gate by simply taking 1 minus your input. So if you put in 1, you get 0. If you put in 0, you get 1. And an OR gate, well, that's just fish in a barrel because the vertical bar is an OR. So you just do that. However, then I got to the AND gate and things started going seriously wrong for me. The AND gate, using only the straight line things, is an utter bitch. It turned out to be a lot easier to do an AND gate, which is fine. So an AND gate is just not X and Y, which expands out to not X or not Y, by De Morgan's. And so I have X or Y, and then I get 2 knots, and I put them in there, and now I have not X or not Y, so I have an AND. And then all I have to do is put a knot out in front of it, and I've got AND. I tried to do that, and it didn't quite work, because of course the precedence was wrong, so I had to put parentheses in, and of course parentheses are a big no-no, because they're not little straight rods. But of course this is perl, so there's no such thing as an impossible task. It turns out that it's relatively easy to do it with straight rods, you just do this instead. What this is doing, for those of you who can't see it straight up, is it's taking the NAND and it's putting it into an array constructor, and then it's accessing the 0th element of that. And that's the AND gate, and if we run it, indeed 1 and 1 gives me 1. 1 and 0 gives me 0, and 0 and 0 gives me 0. And of course, once you've got those 3 basic components, writing any program is then just a simple matter of programming. But even for perl, the readability was just a fraction suboptimal. And the programs, I have to admit, did get a little bit too hard. Program that just prints 42. So I felt that if I was going to show you real programs, that might make the talk run on even longer than it's going to anyway. So I had to accept that progress occurs through failure, and I had to write that off as a failure. So what would I do instead? Well, I'd have to backtrack and try something else. And so I went back to historical perspective because that's what Rommel would have done. And I thought, well, in 2000 I did Perl and quantum mechanics. In 2002 I did Perl and general relativity. In 2008, hell, I'll do Perl and quantum mechanics and general relativity. Because it turns out that there's a long, glorious history of this. If you go back 80 years to 1928, they were already doing quantum mechanics and general relativity together. In particular, this guy. This guy is Paul Dirac, who was a giant of physics. And as you can see, he too was experimenting with the idea of rod logic in Perl. But when I say that he was a giant of physics, I don't just mean that in terms of his intellectual attainments, I mean he was physically a very, very tall guy. So here he is with Ernst Rutherford, who was 6'5". Here he is with Japanese scientist Hideki. Here he is with Einstein, looming. Here he is with Bohr and Schrödinger. Here he is at the Copenhagen Convention. Can you spot him? Here he is next to Michael Jordan. And of course, Larry Ward. This is a big, tall guy. And in 1928, he came up with a big, tall equation. Now, I wouldn't insult your intelligences by presuming to explain this to you. I'm sure you did it probably in high school. But, you know, in case there are any people that don't follow it, this basically says that the rest energy of a quantum particle and the kinetic energy of the quantum particle multiplied by the probability function is equal to the derivative of the probability function against time multiplied by Planck's constant. Whenever you see Planck's constant, that's just a really, really, really small number. And at this point you realise that he was just having everyone on because you have to also multiply it by I, which of course is the square root of -1. At which point I think he probably could have just put a bicycle in there. The thing about Dirac's equation is that it describes the behaviour of the elementary spin-half quanta under relativistic motion. And the reaction is, well, yeah, so what? Until this point, quantum mechanics and general relativity had not been reconciled at all. They're still not reconciled properly, but there was just nothing joining them at all. In this equation, you have both quantum mechanical components and relativistic components. All in the one equation. And it's predictive. If you solve this equation, you get two positive energy solutions, and they turn out to predict very precisely the behaviour of the two spin states of the electron. So it was useful. The problem was, it turned out there were also two negative solutions, and no one could know what to make of them because they would have been anti-electrons of some kind. They turned out to be the positron. Well, they probably should have called it the bizarrotron. Because it's just plain strange. Negative energy, you know, you go up to a positron and it sucks the life out of you. It's the vampire particle. And in addition, it's got negative momentum. What the hell does that mean? So 4 years later, this guy, Carl Anderson, who was obviously getting far too involved in his work, I believe he was in fact the world's first bionic man, but not very successful. You know, miniaturization hadn't come in. And he developed a device that he called his ballistoscopic observatory of neutral gases. Now some people believe that this may not in fact have been a physics device. But he claimed that using this device, he was able to take pictures of positrons. And this indeed was the first picture of a positron ever taken, allegedly. And of course nowadays, positrons figure very strongly in medicine because they're the basis of positron emission tomography, PET scanning, which allows you to scan your pets, and also terribly important because it's the fundamental basis of AI, being the technology on which all brains of robots are developed. So what about this negative momentum? What was that all about? Well, to understand that, we have to fast forward to 1948, and this guy. This is Richard Feynman, who is probably the biggest beatnik fail of all time. And he was on his own certain substances because he came up with this diagram where space goes down the page and time goes across. And he realised that on this diagram you could draw the interactions of any series of particles. Here we have a particle that's moving down through space, and at a certain time it emits some kind of piece of the radiation, and having changed its momentum by emitting that piece, it now heads off in another direction. And you can do more complicated ones like this. The most famous of these, and they're called Feynman diagrams, was developed by John Ellis, who was at CERN in 1977. And I swear to you, this next bit is a true story. Everything else to this point has been crap, but this is true. In 1977, he's in a bar playing darts with a young female co-worker. And on a drunken bet, he bets that if she can beat him at darts, he will put any word she chooses in his next published paper. She kicks his butt, and the word she chooses is penguin. So he's scratching his head, and he tells the story himself. He went home and got high. Swears it all through. And when he came down, he realised that his next paper was going to be about the transformation of antibody quarks from strange quarks through W boson emission. And of course, if he drew the map like that, it looked like a penguin. And now the physics literature is totally full of penguin diagrams. It's an actual recognised jargon in the literature. Meanwhile, this guy is now on his own certain substances, and he realises something interesting about his diagrams. He realises that the diagrams are physically accurate to the behaviour of the particles, and if they are, then you can rotate the diagram with respect to the space-time axes. Remember, we only have to change the velocity to do that. And they stay accurate. And it doesn't matter how you do it, they stay accurate. Now, most of us would stop there. But Feynman did this. Why is that weird? Because now the particle is going back in space, and it emits such a powerful burst of radiation that that knocks it backwards in time. And this was just kind of a mathematical curiosity of the solution of the equations until someone looked at it and said, you know what? If that particle going forward in time was an electron, then the properties of the particle going backwards in time really do look an awful lot like a positron. And so this weird idea was born that a positron is just an electron that's moving backwards in time. And of course, as soon as I saw this, because with superpositional values, I had created programs that ran in constant time. With time-like loops, I had them going in zero time. If I could somehow build variables not out of electrons like everyone else does, but out of positrons, so what is one of these positronic variables? It's not a very complicated idea. Your regular variable goes from the point in the scope where it's declared to the end of the scope. That's its lifetime. Positronic variable, exactly the opposite. Its value that it stores evolves from the end of the scope back to the point where it was declared. So in other words, we take a little program like this. This one is just converting Celsius into Fahrenheit. And it's just regular variables. I have a lexical variable called temp, and I initialize it with 37. Then I do operations on it, and that changes the value in it, going forward through runtime, and eventually I print it out. And what I'm suggesting is that we need to have a second kind of variable declarator, and I was going to call it PV, the positronic variable. And when you have a positronic variable, then its lifetime would start at the end of the program, at which point it would be undefined, and that's what we would print out. But then it would evolve back through the program, doing the operations, and of course all it would be for naught, because once you got back to the initial assignment, it would just assign that back. So it was kind of looking like this wasn't going to be so useful after all, until I realised that that's not how you write a positronic program. You have to think four-dimensionally. So what you do instead is write it like this, where you declare the variable and then immediately print it. Because the variable's lifetime would start down here with a sensible value, it would go through the operations required, and then it would print out. Now, of course, that's from the viewpoint of the positronic variable traveling backwards in time. From our viewpoint, it's simply you start the program, it prints out the result before it did the calculation. And I think the economic model that we need for this has to do with something more like this, because you don't have to have fixed constants being assigned to these all the time. It'd be much more useful if you just put a read line down there. And then, of course, you would read in your value, and just as soon as you start the program, it would tell you the Celsius equivalent of the Fahrenheit temperature that you are going eventually to type in. Except we wouldn't use it for that, we would use it for Google stock price. Now, you can actually do serious computation with this kind of technique. You don't have to have a read line at the end. If I read in a number to n, then I can declare an anti-square root variable, and I would simply assign whatever eventually going to be in that from the future into my square root and immediately print it. And then at any time later in the history of the universe, I can simply compute the anti-square root. Now, it's really easy to compute the square root you're sending back in time if you've already got the one that's coming forward in time. You can take advantage of very elementary mathematics. For example, the fact that the square root of a number is the same as the number divided by the square root. It's the definition of a number. So you can just do a simple calculation where you took the square root that you already know from the future, and you added that to n over the square root, and took the average of those, and then sent that in the positronic variable back in time to be printed out. Now, a more complicated and useful example of that would be, before I do that, here's a diagram of the flow of the data. So if I put in the value 25, it travels forward in time in the regular variable, getting printed and getting used in the calculation. And here's the second regular variable traveling forward in time, and it gets its value from the positronic variable. And it goes forward in time, and then I do 25 divided by 5 is 5, plus 5 is 10 divided by 5, the 2 is 5, and I send that back in time to be the correct answer. This, of course, is a Feynman diagram for your program. In the future, all programs will need their own Feynman diagrams to understand them. So, for a more useful example, here is the binary chop search algorithm implemented in negative time. So, everyone's familiar with binary chop? You have a sorted list of values, and you just guess where it's going to be, the one you're looking for. You just take the start and the end and you say, that's my maximum, minimum possible. I'll just split the difference and try the middle one. And if the middle one is too big, then I'll move the maximum down to there, because it can't be any bigger than that. And if the one you check is too small, I'll move it up. And wherever you go next, you just split the difference again and you search there. So theoretically, it's a log n search algorithm, but not this way. Let me just quickly show you the Feynman diagram for it. I'm sure you already had it mapped out in your head. Let's have a look what goes on here. So I have three positronic variables that are storing the boundaries and the next guess. And so for my initial position check, I just take the next guess that's going to come back in time for me. And if I happen to be in the right position in the list and it matches the target, then I simply print the answer. And of course, I have to remember to send the correct answer back in time to myself. Which brings us back to Keanu Reeves. On the other hand, if I don't happen upon the first case, I'm going to do the else. And the else has to, of course, work out, do I move the max down or the min up, and do I average the two? But the important thing is that you have to do it backwards in time. You have to move your boundaries after you use them to compute the next value, because the boundaries and the value are moving backwards in time. So if I ask for camel, for obvious reasons, then camel goes forward in time, and if it's equal to the target, then I print it out, and if it's not, then I compare it with the target, and I take my positional value, which is 1, and I add 1 to it, or I subtract 1 from it, and then they both go backwards in time, and I average them out and send that backwards in time up to the position, and sure enough, 1 is in the sorted list where camel is. And of course, it prints it out before it does any of the work. So I guess you've picked up on the pattern and you know the next bit. Yep, I implemented it. So here is that square root anti-square root example. And all you have to do is use my positronic variables module. And when you run that and type in a number, out it comes. And if you type in a different number, the right answer comes out, and if you type in a different number, the right answer comes out, and blah, 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 blah. So it just executes the code, sending some of the information back in time to compute the square root. Here, for example, is the binary chocolate camel program, and it does the same thing. I've changed the printout so that it actually looks nicer. Not in the code, obviously, but when it prints out, it's going to show the whole list and an arrow where you're going to match. So if we run this and ask for camel, it finds where the camel is. And if we run this and ask for dog, it finds where the dog is. And if we ask for mouse, it says there's no mouse in the list. And indeed, there is not. So here's the source code, and I wasn't sure whether I'd take you through the details of the source code. It's actually not very complicated. All that it does is it just goes into one of these temporal loops, and while space-time has not converged on a consistent Feynman diagram, we reverse the arrow of time and then run the events backwards. And then we check the convergence again, it hasn't, then we reverse the arrow of time and run them forward again, and we just run them round and round and round until the universe converges on the correct answer. It's very straightforward. Checking for reversing the arrow of time, of course, just means changing the direction of entropy. Very straightforward. Checking whether time space is converged, the real thing that this module does is it changes any positronic variable that you create so that the positronic variable tracks its own history through the timeline. And so all I do is I track the history forward through time, and then I run it backward through time. And running it backward through time is just a matter of subtracting 1 from the indices. Because if you're going forward in time, then when you do an assignment, the value persists thereafter. But when you're going backwards in time and you do an assignment, the value persists beforehand. So what you have to do in these positronic variables is look ahead in the timeline to see what the next value would have been, and that's the value that it is before you do the assignment. So all I do is I go around and check the convergence of the timelines of each of these variables. And I take the second most recent and the most recent timeline, and I look at each of the states in them, and if the states are different, then I have it converge, and if they're the same, then I have converged. And then all the rest of it is simply the matter of implementing those variables that track your own timeline. If the variable's moving forward, if entry is greater than 0, then when you do an assignment to it, you just push onto the timeline the current value. But if you're running backward, you just use the anti-state, the previous state, and nothing else needs to be done. By the way, that's the real code. I didn't make that is the actual code. I just find it easier to write impossible code by just saying how I want the universe to be. So, when I was developing this, once again, the progress by failure struck. Because when I first wrote this code, I made a very obvious mistake. And when I show you, you will groan at the obviousness of it. When I wrote this, I thought, well look, if I actually get the correct position on a guess, then I'm going to print the thing out and finish the program, so I don't need to send the thing backwards in time. So I can remove this statement, which of course in the Feynman diagram just removes this transition. And things still seem to work. But what I neglected to think about was the fact that when you have an if and an else, if you happen to luck onto the correct answer first, then the else will never run. Which means that all of that code doesn't get used, which means that none of those transitions occur, which means that all of the positronic variables start with undefined values which propagate backwards in time and then get propagated forward to the ordinary variables and come back down here and you end up not printing anything. Well, damn. You know, okay, rookie mistake. I needed to put that back in so that even in the correct universe, it sent it backwards to itself. So I felt that that was a very important observation about these kinds of programs, that the positronic program is only going to work for you if the Feynman diagram of it is self-consistent. That is, it will only work if it will always have been working. Both forward and backward in time. Now, real positrons, of course, don't have that problem because the Feynman diagrams of real positrons are always self-consistent because positrons always meet electrons at collisions and annihilations because a positron is just an electron that's being sent backwards in time. So it's not possible for it to be inconsistent. But of course, electrons and positrons are much more reliable than human programmers. But that to me was philosophically worrying because this Dirac equation assumes that this static four-dimensional space-time where you can send things forward and back in time and they're just fixed as they are. And moreover, the Feynman diagram says that space-time is this static phenomenon that you can rotate to any angle and it will still work. So the electron-positron interaction will always have had been being exactly as they shall have been being. And inconsistencies can't happen because they already didn't. But this must have been extremely worrying for the philosophers. Because where is free will in all of this? Einstein, you know, if everything will have had been already happening, where's our choice in the matter? Einstein talked about this where he said, look, I don't believe that God plays dice in the universe. And that's true. God doesn't play dice with the universe. God plays dice with multiple universes. So, for example, if I have a little positronic program like this is even simpler. All this does is have one positronic and one ordinary variable, and we assign the negative of the anti-variable to the positive one, send it forward in time, and then send its negative back. So the diagram of that just looks like this. And it goes round and round and it's all very happy. But as soon as you show this program to a hacker, what is the first thing that they will do? They will remove one, but only one, of the negative signs. And then we have a problem. Because on the reverse assignment to the anti-variable, we now don't have the negation. So now it goes back positive in time, and the negation on the forward makes it negative, which goes forward in time, and then it gets assigned without negation backwards in time, and we have a never-ending cycle of it never settling down, raising kids, having a life. It just goes round and round and round inconsistently because we let a hacker at it. And of course, if you do that, the hacker will think, that was cool. Let's modulate 3. Because now there'll be 3 separate states that it doesn't settle down in. And it'll just go forever. So it's going to be intrinsically self-inconsistent. I thought, this is going to kill this. It's not going to be a useful technique. Until I realised that it's only intrinsically inconsistent in a single universe, in a single space-time continuum. So back at the Copenhagen Convention, they came up with a Copenhagen interpretation, which I told you about before. If it can be in different possible states, it's in all of them simultaneously. And everyone basically signed off on that, except this guy. This is Hugh Everett III. And you can tell by looking at him that he's a troublemaker. He came up in his PhD thesis with a many worlds interpretation, which said that a particle can be in many different states at once. It's really only in one state, but in a different one in each of many parallel space-times. And this resolves our problem. As long as I can have many parallel space-times, I can have a Feynman diagram that is static and self-consistent. So when I have that bad program, the Feynman diagram for it actually looks like this. There are 2 universes with 2 Feynman diagrams, and we have a little bit of crossover between them. And if you follow that around, you can see that you have the same behaviour, but now there's no need for dynamics and there's no need for an infinite continuation of change. And of course, if you want 3, you just get 3 universes. It's very straightforward. Note that if you follow things around, you find that there is a single closed time-like loop where the path returns eventually through loops in multiple universes to itself back in the first universe at the same time. So we call these closed time-like curves, and in 1991 this guy, David Deutsch, proposed that the 2 views of the universe, the Copenhagen interpretation of the many worlds, were in fact just 2 different ways of looking at the same thing. He said that if you look from the right direction, one of these multi-universe closed time-like curves looks exactly like a superposition. So in this diagram, if I don't stand here and look at them kind of side on, if I gradually move around and get a better perspective on them, then eventually from a certain angle, they look like superimposed values in one universe. And 3 do the same thing, but now you have 3 superimposed values. So there is a way to preserve free will, which will make the philosophers happy. And more importantly, positronic programs can always be consistent, and they can have been always being consistent, as long as I'm allowing my anti-variables to be superimposed across all of the possible time-like curves in as many parallel time spaces as I need. In other words, now, fortunately, it wasn't too hard to code that in. As it turned out, all I needed to do was jump down to my convergence criteria and say it's no longer enough that two adjoining space-times agree on their view of the Feynman diagram. What I now have to do is iterate back through all of the timelines that the particle participated in until I find an older timeline that matches the current one. Because if I find an older one that matches the current one, then what I've found is a series of time-like loops that eventually bring me back round to the first. And that's all that code does. And then the other thing that I need to do is, when I'm looking at the values of the individual variables, I need one extra case. That extra case is, if I find that the timelines have converged, but they have converged in more than one universe, then I need to go through each of the variables, and for each of the states, I need to put the variables' multiple states from all its different universes into a single quantum superposition, an any, in the code. And when I do that, then my ordinary program, which goes forward by negation and back by negation, works exactly as you'd expect. You get a consistent Feynman diagram. But now when I do the bad version, instead of looping forever, it now just says, okay, then the anti-value is the superposition of both 1 and -1, and the value is 1 or -1. And of course, if I do it modulo 3, then I get 3 states in my superposition. And if I do it 11, then I get 11 states. You don't always get as many states as there are modulo, because if you do it with a number that has many factors, then they factor out, you only get a fewer number of loops. So in conclusion, if you take quantum mechanics and general relativity and perl, and by that I mean Dirac's equation and Deutsch's closed time-like curves and line hacking, then you can create programs that run in negative time in as many universes as necessary. All simply because of those time reversing properties of the spin-half particles under relativistic motion. And that's where the title of my talk came from. Now, observant people will notice that that's not actually the title of my talk, and will be asking themselves on their blogs and on Twitter, what happened to the virtual nanomachine programming? Well, I did show you that earlier with the little nanomachines, but it didn't quite work, did it? Well, I thought I can't leave it there, I've got to do the whole talk. So I took the square root program and I translated it to I have to tell you, that was a bit of work. But when you run it, and just because I wasn't happy at leaving it there, I figured I'd better deal with that other bit of Dirac's equation as well. So when you run this version, and you put in that,